Well, there's my face. Okay. Very good. Okay, a couple of clerical notes. First of all, I've never given a seminar where everyone's on a sofa, so this is pretty exciting. But really what I want to say is thank you very much to the organizers. Connie, thank you for the invitation. This is really a special environment. I really like these smaller coffee-centered shows. It's really where I actually learned how to speak about coffee to the professionals. So thanks for putting this on. For those that traveled from outside of this beautiful state of Oregon, thanks for making the trip. It really is going to be a pleasure to meet with you. I'm here both days, really excited to get to know you a little bit. And then the final note I want to make is that you don't get to my size by talking through lunch, but after I speak, we have lunch. So I'm going to do my best to not run into lunch too much. With that, what I'm going to tell you about is some of the research that's done in my laboratory at the University of Oregon. UO is about 2 hours south of here in the city of Eugene, and I actually don't do any of the work myself. So I'm going to start by just noting that all of the work is done by my wonderful research group here, and most of the work today is going to be from Robin Bumbaugh, the student who is leading the coffee lab, as well as the 3 undergrads, Lena, Eli, and Julio. During COVID, we created a space which I'd say is a humble public environment here, and what it is basically a cafe that is no money changes hands. You're free to come over and you can try the experiments that we're working on that day. The coffee's donated. We try with the small amount of money we have allocated for coffee purchases to be mindful about who we choose to spend that money with to support underrepresented businesses. We try to think broadly, but also we solicit the donations because I don't want to put my preference of coffee into my laboratory. I want to think broadly about what coffee means. This lab has produced 2, I'd say, relatively well-known papers. In 2020, right before COVID lockdown, we had this paper that resulted in people pulling faster espresso shots. And then at the beginning of this year, actually around Christmas, perhaps last year, we had this paper on triboelectrification and mitigating charging during coffee grinding. But as noted in my intro, I am the author of Water for Coffee with Maxwell, and we promised you a second edition. I can tell you that this is the second edition. We have a cover, we have an ISBN, it's coming this year. And can I just see a quick show of hands who read this book, the original one? Yeah, and was it challenging? Yeah, okay, here it is in 2 slides. All right, so metals extract flavors, but for every plus you have to have a minus in solution. And the biggest problem in terms of flavor is bicarbonate. So bicarbonate is a buffer, it's this species here. When you add acid to it, it turns into carbonic acid and then decarboxylates to form CO2. If you were to add base to it, it would turn into carbonate. Carbonate will then go off to react with calcium to form limescale. So either way, one side, it destroys the flavor of acid. The other side, it's basically turning into limescale and destroying your machine. It's a bad actor. The result of it is this. On the left-hand side is the SCA flavor wheel from 2016. On the right-hand side is what you get as you increase carbonate hardness. These are the panels that drop out. I had a student go through and map out all of the organic compounds that correspond to the flavors of the natural products on the outside of the wheel. And then we basically used a little bit of math to determine how significant the impact of reaction with bicarbonate would be. There's a logical fallacy here because who's to say that the flavor of blueberry in a real blueberry is indeed the thing that gives rise to the flavor of blueberry in a coffee that you'll taste. So of course it's not exact, but more or less it shows more or less what you'd expect from having hard water brewed with specialty coffee. Okay, that's water for coffee. Good. So now let's get to business. Okay. So in order to understand where I'm taking you on this talk today, we need to go through a series of Nobel Prizes. Let's start with the Nobel Prize in 1907 awarded to Buchner for the discovery of the enzyme. Buchner's observation was that if you ground yeast cells, they were still able to perform fermentation, which meant that there was something smaller than the cell that was doing chemistry. And that observation led to the wonderful invention of wine, which I love. Oh, excuse me, we got too far here. This wine right here. And the observation with wine is that when you have grape juice, you're starting out with about 15% sugar water, and you're going to convert that sugar water over time into ethanol water. And because one molecule is turning from glucose or fructose or whatever, sugar, let's say, into ethanol, you can monitor the change in refractive index and change in gravimetric density over time. You'll see that they track. So the density is the white circles here. You see it, you start out at relatively high density, and density will drop, and after about 7 days, you see a plateau. It takes about 7 days to ferment all of the sugar into ethanol, so that's what you're really seeing there. And the observation then was made that the refractive index tracked with that. The refractive index, of course, is the effective speed of light in the material, and it seems to more or less correspond to that of the effective gravimetric density. But there's a problem. If I look at just 3 different compounds, sodium chloride, which is just table salt, glucose, and ethanol, I can add about 4 weight percent ethanol to a solution and get the same optical response as that of 1 weight percent salt. So I'm not able to use a refractive index measurement to tell me whether I'm drinking ethanol water or salt water. Yet, here we are, okay? So there's more than just one compound in coffee, there's thousands of them. And we use a device which measures refractive index and relates it to the total dissolved solids, or the amount of coffee material floating around in solution. And then on the x-axis, you'll see extraction yield, which is an interesting parameter. That's the amount of coffee that you extracted out of the dry mess as a fraction. And so this is actually an efficiency metric that has something to do, I can't see the laser. I am contractually obligated to use a green one, right? So, okay, good. So extraction yield is an efficiency metric in my mind. It's how much stuff you could get out for that given brew parameter. Whether it tastes good or not, we'll get to that in a minute, all right? Okay, so then to understand another problem, we have to go to the first Nobel Prize ever awarded to Van't Hoff. He made the observation that if you change the temperature of a chemical reaction, you're going to change the product distribution. And I'm going to give you a coffee example. If I use cold water to extract coffee to equilibrium, let's say 10 minutes, what I'll find is I'm only able to, in the case that I'm showing here, be able to extract about 9 milligrams of caffeine per gram of coffee that I use. But if I use hot water, I'm able to then extract something like 15 milligrams of caffeine per gram of coffee I use. And no matter how long I let the coffee steep in cold water, I would never be able to get more than that 9 milligrams because we've controlled the equilibrium constant, K, with temperature. This is Van't Hoff's observation. The thing is that not every molecule in solution responds to temperature the same way. So for example, with caffeine, as I increase temperature, I can see I get more out. And so therefore, we call this an endothermic reaction. We need to add heat to push it forward. But other compounds like caffeic acid, which is a decomposition product of chlorogenic acid that you'll find during roasting, this compound seems to extract more or less to the same amount independent of temperature, which means that if I change temperature and brew to equilibrium, I can invert populations of compounds. That's a problem. Okay, good, yeah. So then there's some lovely work from Shahan Yaretzian out at ZHAW in Switzerland, and he looks at a different side of this. He says, okay, we never really truly brew to equilibrium though. What we do is we stop at some point along the way. And no brew method exemplifies this better than espresso, where you might take a lightweight compound like these two right here, and you'll see that very rapidly in the espresso shot, you're going to reach a maximum extraction, and then you're going to start to see the amount making its way into solution is declining because you've reached a rate in which you're extracting it as fast as possible, but that material can't make its way to the surface of the coffee fast enough. On the other hand, something heavy will move much more slowly, and so you see as the longer we extract, the more we get out of it. And that's fine, except for what if you change a parameter such as brew time or shot time? So at this point then, we've extracted a ton of this small molecule, and we're starting to get a fair bit more of this. But what if we then stopped it at 10 seconds? Now we've got a ton of this stuff and basically none of that. And so this right here is kinetics. This is saying that different molecules take different amounts of time to make their way into solution. And if we combine those two slides that I just mentioned, one to equilibrium is thermodynamics, and this one here is how long it takes to get there, which is kinetics, we have a problem. And yet, in our 2020 paper, I parameterized all coffee material making its way out of coffee to the surface of the coffee and being extracted by one set of parameters. In other words, I took an average, much the same as a refractive index device more or less is implicitly doing. And in doing that, I can say, okay, there's a diffusivity constant here and the rate constant for all stuff moving through solution. And that is obviously, that's obviously not right, because I can give you one example here where if we just look at the diffusivity constant that's known for caffeine, 2.4 times 10 to the minus 11, that number is much smaller than the average diffusivity constant, which means there's a lot more stuff that is dictating the extraction of flavor moving much, much more readily into solution than that of caffeine and other compounds. And the other compounding factor is that the small stuff and the large stuff, at least by first approximation, I should say the small particles and the large particles of coffee, are more or less the same material. Now, there's a discussion whether that's really true or not, but at least for now, let's assume it is. That means they get wet at the same rate. And so the water going in, the extraction coming out, you can see then that there's going to be a large portion of a boulder that's not even wet by the time the central piece of the fine is wet. Now the extraction process is limited by that diffusion outwards. Okay, so obviously very complicated. And then we have to measure the particle size distribution to understand how big these things are. And actually, Rob did a wonderful job of introducing this concept in the first talk. So we have a laser diffraction system. It sits on, this used to be the physics break room like counter where they'd eat lunch, but you know, it's mine now. So, so this is what we get out of it. Okay, so you grind, when you start at an arbitrary grind setting and you grind finer, the big pieces get smaller. But the other observation is that the little pieces, the fines, they don't get smaller, they just increase in population. We can understand this because every time you crack the coffee, it makes dust, and the more cracks you have to make, the more dust you make. And so you end up with this nonlinear relationship where as you grind finer, you end up with a lot more fines. So this makes it really difficult to dial in. Now, I do want to note here that there's two little bumps, and it says we'll come back to this if we have time. Well, we do have time. We're going to do it right now. So this is that paper, okay? And in this paper, we basically just fit these parameters I just mentioned, and as a result, we were able to start predicting the output of espresso extraction. There was a problem because our model is in blue, okay? And at some point, experimentally, what you'll find is you start grinding finer and finer and finer, and then your extraction yields seem to go down, the variability goes up, and you have problems with achieving TDS consistently and so forth. And it gets worse is that whenever we were doing this, the baristas would tell me this was the tasty point. So in that paper, all we said was, well, if you only care about extraction yield, just grind much coarser. You're going to hit the same extraction yield, but more consistently. But everybody in this room probably tried this or had someone try this, and you tasted it, and you know compositionally they're dissimilar. Okay, so there's a bit of a problem. And then we said, well, why don't you just use less coffee? Because if you use less coffee, then you end up with higher extraction yields by definition. And so then if you did both of these, you could iterate so that you'd arrive at less coffee, but more efficiently extracted. So in principle, you could arrive at the same strength or TDS, but more efficiently. But they didn't taste the same. So why do we get this volcano? Well, actually, 4 years later, we had this next paper. This is basically inspired by things that almost all of you already knew, which was this idea that coffee charges when you grind it and makes static electricity. And the apparatus you use to measure this is actually borrowed from the volcanology department, where they're studying particle charging emitted from volcanoes. And the reason they care about this is you can put a probe a long way away from a cloud that's generating a lot of electrical charge, and when it discharges, it tells you something about the topology of inside the cloud. So you're able to then understand the shape of the eruption from a remote distance. So all we did is we took their same apparatus here, and we flipped it upside down so that particles would enter charge from above rather than from below. And then you apply electric field, and the negative pieces move towards one pole and the positive move to the other, and you can start to back out the charge and weigh it. And if you took a microscopy image, you'd see that boulders are here, but they're stuck, the fines are all stuck to the edges. So this is a problem, and we think it is these sort of aggregates, or as what did James Hoffman call electroclumps, these electroclumps that are causing problems for when you grind really fine, you make a lot of fines, they cause these aggregates to form, and no longer are you able to evenly extract. This paper was not really about that, it was about ways to minimize that. And borrowing from an old trick that I guess is known as the Ross droplet technique, you can just add a little bit of water. And what you'll see then is that without any water, you have this clumping region, which is a long tail of large pieces. That's one boulder with a bunch of fines stuck to it. But if you add water, the charges never form. And so as a result, the little pieces and the big pieces come free from one another. So you'll see then that the tail disappears with a little bit of water. You get slightly more of the boulders and ever so slightly more fines because they're now separated. And it does depend, of course, on a variety of things, but to really highlight one of Rob's key things that he mentioned is this moisture content. Actually, this is basically related to the amount of moisture inside the bean and also outside the bean. So the more wet the bean, the less charge. So as a result, generally, it was lighter roasts didn't form as much charge as these darker roasts. But independent of the roast, if you add water, you basically take the charge towards zero. And if you do that, you're then able to brew more efficiently at finer grind settings. And we went on to show that was important. But the one thing we did not show was how do we assess the composition of coffee in real time? Because thus far I've always been talking about extraction yield and TDS, and yet I know that that cannot do what I want it to do as a chemist. It does not give us that level of fidelity to say this coffee should taste exactly the same as the next one. Okay, so to get to that, we have to go through some more Nobel Prizes. All right, Arrhenius, 1903, very simple observation. If you take salt and dissolve it in water, it splits into sodium plus and chloride minus rather than sodium zero and chlorine. Obvious now, not then, okay? Then we have Nernst, who showed, basically backed out the fundamentals of pushing reactions forward. And you can think of it like catalysis. And then Langmuir talking about the interface between a solid and a liquid. And then fast forward to 2019, where the Nobel was shared between these three for the development of lithium-ion batteries. This is a subset of a discipline known as electrochemistry. Now, electrochemistry is defined as a chemical reaction where an electron, a negatively charged, very lightweight particle, is transferred. That's full stop. That's the definition of electrochemistry. And I'll explain it to you in some detail. All right. So let's start out with the most simple atom, hydrogen. It has one proton, which is positive. It has one electron in its orbit somewhere. It's negative. And that electron occupies a very well-defined energy level. You can think of this classically as a positive charge and a negative charge are attracted to each other to some extent, but then quantum mechanics adds some other confusing stuff. So we'll just simply say that electron has some well-defined energy. And as you apply temperature, that well-defined energy sort of spreads out. You're going to have a distribution, but nonetheless, this electron occupies this energy here. And it also has some probability function associated with it. So it's very likely you're going to find one electron, which is negative, near something that is positive. Okay, if you apply energy to this system that is equal to this difference, you can promote the electron from here to here. And when you do that, that electron now occupies a different shaped orbit. It has a different probability function. They may overlap in space a little bit, but the point is they're at a different energy level. And you've actually seen this before. So when you look at the sun's spectrum, the sun emits almost white light, but it's not quite white light. There's a few things missing in there, a few colors. Now point to specifically to the C23 and the C24 band. C23 is red, C24, the F band there is blue/purple. And what this corresponds to is the energy gap between going from 2 to 3 and 2 to 4. And so that 2 to 3 is a lower energy, so it's red light. The 2 to 4 is a little bit more, so it's blue light. Those happen to correspond to the wavelengths that we can see. And the reason that it's happening for hydrogen is because it turns out the sun is made of hydrogen. So the sun is creating this light and the material it's made of is absorbing it, okay? But there's another example that happens on Earth. So this D band right here. So in the case of the D band, that's a sodium band. So when you heat up a sodium filament, it's going to emit light at that sodium band wavelength. And that's what these traffic lights are made of, street lamps are made of, or emit yellow light because they have a sodium filament. All of this is to say that electrons are negatively charged and they move between well-defined energy levels, and those energy levels depend on the atoms they're bound to. So sodium is different to that of hydrogen, hence they have different colors that they absorb and emit. So now let's start with a really simple electrochemical reaction. This is one where you have an acidic solution. So this is a piece of platinum, and you have water floating around up here, and it's acidic, so there's protons in there. If I add those electrons to this solution through this piece of metal, what you'll find then is that those protons will combine with those, electrons will combine with those protons to form hydrogen gas. And so basically you can imagine as water comes by, sticks to the surface, those protons are now stuck, you add electrons or electricity, they come together, and they are released as hydrogen gas. This is a really important chemical reaction, probably one that's going to change our lives, because this is the backwards reaction of making a hydrogen-based economy, or 1/2 of a fuel cell. This is moving away from basically burning fossil fuels and doing something more sustainable. But I mention it because this is a really important reaction. We're adding electrons to something. So we call that process a reduction. an electrochemical reduction. You've heard of the opposite, which is oxidation. An oxidation reaction is when you lose electrons from something. And so an easy mnemonic here you'll never forget is an oil rig cap, which is at the anode. You can forget that part, I suppose. Oxidation is loss. Reduction is gain at the cathode. Okay, yeah. So reduction is gain of electrons. This is me trying to say something's going in. This is oxidation, something's coming out. And this is the process that we talk about when you're talking about something tasting oxidized. It's because it's reacted with oxygen gas. It's lost electrons. It's turned into a new molecule. But in the electrochemical sector, we use this very specifically to try and generate electricity. So if you think about what a lithium-ion battery actually is, it is the observation that lithium wants to lose an electron to become lithium plus. And when it does that, that electron can produce 3.03 volt. Therefore, if I string these together and create a closed circuit, I can allow lithium to lose its electron and move, and as a result, I generate electricity. And that's the basis for technologies like what we see in this vehicle. But let me show you on a sort of a schematic scale. You start out with lithium 0 on this side, and as you start to connect the load, those ions, the lithium ions, will move to form lithium cobalt oxide or some other material, and the electrons will go around the circuit. And when they do that, eventually, you're going to have no more lithium ions over here. You're going to have them all over here, and you've generated all of your electricity. No more electricity is available because there's no lithium. So to recharge, you then got to push it backwards. So you got to apply the equal but opposite force to push it backwards. The lithium ions will diffuse back over here and become lithium 0. And therefore, we can conclude then that if something has the ability to produce electricity, it must have the ability to produce a positive voltage. And if something is has a potential that is negative, such as the backwards reaction, then that is going to require an application of electricity. And you've seen this before, so I'm sure that people have used a multimeter before. Basically, you take this device, you connect it, it closes the circuit, and you're able to measure the voltage that this material is capable of producing. So this is a AA battery producing 1.2 volts. All right, let's talk about Breaking Bad for just one moment. So the standard chemical reaction we just mentioned was hydrogen plus electrons goes to hydrogen gas. And we define that as producing 0 volts. It will go forward and backward at making basically no energy whatsoever. And you can then see here that if you want to try and spontaneously unrust something, think about that. Things tend to not unrust, okay? You're going to see then that iron 2+, let's call that rust, needs to go back to steel. That's got a negative voltage. And so as a result, that's not going to happen spontaneously. Instead, the other way happens. Iron turning into rust happens, and the reason it does is it creates a voltage. The same thing is true for zinc. Zinc will rust spontaneously, and as a result, you're going to get even more voltage. And so what a galvanized nail is you take iron and you dip it in zinc. And then when you pull it out, the zinc will rust preferentially over the iron. And when zinc rusts, it turns into zinc oxide, which is a white powdery material. A galvanized nail is just steel with a zinc layer that's rusted. And so the zinc protects the steel. Good. The key thing here is that they happen at different voltages. In Breaking Bad, they took those nails and they said, oh, we're going to take the zinc coating off of this nail, which is able to give us about whatever it was, plus 0.76 volt to go forwards. And we're going to take mercury out of brake pads, which gives us plus 0.85. When you can combine those two chemical reactions, you get 1.6 volt. And if you strap them together, you get yourself 9 volt and you can start your car. It turns out I had dinner with the chemist who informed the Breaking Bad program. That was a fun dinner. And my first criticism went specifically to this. Nobody puts mercury in brake pads anymore. We haven't done that since 1920, I think. And the reason is because if you break your car, then all of a sudden all the mercury is just being emitted into, anyway, she knew that. It was fine. You take your creative license. Here, let's talk about a more pertinent one. This process is where you're taking, you dip a wheel in a solution containing chromium. You're then going to apply a voltage, and you're going to take chromium to chromium metal. And as a result, you end up with a wheel that's shiny because it's covered in chromium. Does anyone know the technical definition of this process? Yeah, well, that is a definition. It's also known as pimping of the ride. But but indeed, electroplating. So, all right. So you're like, where the? I spoke to someone who flew all the way here from Mexico just to listen to this talk, and I haven't mentioned coffee really at all. So I assure you we're getting there. Okay, so a lot of background goes into this, but now I just want to explain to you what the purpose of all this is that I can build a device. You can buy a device. It's a multimeter that you run backwards, where you apply electricity, and you basically are able to control the voltage you're applying and measure the current, which is the opposite of what you usually do with a multimeter, because usually you want to know if I touch this, will I die? That's the opposite of this, okay? So this one, we're going to apply a voltage and measure current. Okay, so let's go to an atomistic picture. So on the left here is voltage applied, and we're going to measure current. Here is a sort of an energy level diagram that we'll talk through as I start to sweep the voltage. This is a picture of the elemental form of this metal that I'm talking about. And this is coffee, let's say. There's stuff, okay? So what we're going to then do is the very first thing is we're going to start applying a positive voltage, which means as we're stripping electrons out of this material. So just go back and forth between them. The energy level of this is dropping, okay? And if it drops sufficiently low that it runs into a molecule that has electrons, it will steal those electrons from that molecule. And in doing so, it will then, a current will flow. We've closed a circuit inside that solution. And so what we'll then see is we'll see a signal. And that, let's say, happens to be chlorogenic acid, where all of a sudden we take the chlorogenic acid to this oxidized form. I have no idea whether this tastes good or not the point at this stage, okay? But we keep going, but then we stop, and so we get our signal, all right? And then we're going to sweep backwards, and we're going to push the current, the voltage back up again. And once this is sufficiently high, it'll give the electrons back to chlorogenic acid's oxidized form and take it right back to chlorogenic acid as if we'd never touched it. So we can close that loop. And the neat thing is that I can touch chlorogenic acid without touching caffeine. But if I wanted to touch caffeine, I could just apply even more voltage to get down to that level down here where we start to oxidize caffeine, which means we're able to then directly make measurements of different families of molecules in solution. All right, this is the ugly version of what it could look like. You just take 3 pieces of metal. I'm sorry that the contrast isn't working here, but imagine 3 sticks of metal and a shot of espresso. And in our lab, as I mentioned, we have the requirement you have to be able to drink the product of our experiments. So these are completely inert metals. I've actually used my wedding band, gold, platinum, these sorts of things. And we say they're expensive when you need to buy them as gifts. But when you need to buy them as just a little piece of platinum to use for reactions, they're actually not expensive at all. It's really, really an affordable approach. Now, what are we measuring? Well, okay, so coffee, there's a lot of stuff in coffee. Let me have some water. Good, okay. And we use this to describe all of that. But it turns out in electrochemistry, those molecules that give rise to those flavors come in groups. Basically, something like a functional group. So that it turns out if we apply something like +1 volt, we're able to get alkyl and aryl amines and enamines. If we apply, I don't know, what is this, -1 volt, we can get to anhydrides. So different types of molecules respond to different voltages. Now, I'm not the first to think of this. So people have used this both on analysis of green and roasted coffee extracts. And there's a nice paper in 2016 which shows that if you just grind up green or roasted coffee, extract it in some way, and you use this DPV, which is just differential pulse voltammetry, or applying electricity and measuring what comes out, you actually get you basically get a good measurement, the equivalent of a high-performance liquid chromatography measurement. So we're able to say how much chlorogenic acid is in solution by just quickly passing electricity between 2 electrodes that we dip into a solution of these extracts. And just as a sanity check, the green coffee here has a lot of CGA in it, and the same coffee but brown has less. That makes sense because we've roasted. Okay, good. So it is able to pick up things that we know to be true, that chlorogenic acids decrease as you roast the coffee more. Okay, so then what we might do is, in my lab, we might create some standard solutions where we start out with just no chlorogenic acid, and as we add more and more and more, we can see a peak grow in associated with chlorogenic acid. The same thing is true for a solution that contains caffeine. We start out with no caffeine, we add more and more and more, and you start to be able to measure it. All you have to do is integrate under this curve, and that is a direct measure of the amount of that material in that solution at that voltage. You can do it with other things too. So basically, if you know the identity of the compound, this is caffeic acid, then you can see. And if you're keeping track, that's at 0.3. This one is at what? 1.4. This one's over here at 0.5. So in principle, we could get resolution that we would require to be able to make statements about quality. And everything's good except for then you do the experiment where you take coffee that you know has chlorogenic acid in it and you add chlorogenic acid to it, and you'd expect to see a feature come in. And this is it. Coffee is blue and chlorogenic acid plus coffee is green, and they're the same. And the same is true for caffeine. And so this got me thinking, well, I saw this one first and I was like, did my students accidentally use decaf? And then accidentally add chlorogenic acid to it. Like I thought these were switch. Anyway, they assured me they'd done it right, and they were right. And it turns out, an interesting observation, that caffeine and chlorogenic acid end up floating around in solution stuck to each other on the atomic level. They form an aggregate. So free caffeine, it gives these features in NMR. We needn't talk about what that is. Just say that these three lines are supposed to be exactly where they are, and if they shift, then something is interacting with them. Chlorogenic acid is here, and when you mix them together, you end up with this shift of caffeine moving over a fair bit. And as a result, this means that caffeine and chlorogenic acid need to be separated somehow before you can actually measure them, which is why we weren't seeing them in coffee. This is an interesting observation, and one that's probably another reason why you don't see caffeine in more pharmaceuticals, because most pharmaceuticals are phenolic, and as a result, caffeine plus the pharmaceutical would not actually absorb into your body as rapidly because it's formed this aggregate. So this is the basis of an NIH proposal that my group is working on that has come directly out of work in coffee. So hopefully that yields something nice. Now, the proof of this is simple. All you do is you start out with a solution that contains caffeine and you add in chlorogenic acid, and what you'll see is the caffeine feature, which is this peak here, seems to decrease, and the chlorogenic acid feature grows in but also broadens out. And so at some point you get to the concentrations of coffee and you end up with not being able to see anything. We can do the counter experiment here where you start out with caffeine, you add in a molecule you think is not going to interact with it, sodium nitrite, and indeed it does not interact. So here's, what is this? This is right here, this is the caffeine peak. It broadens a little bit. This is sodium nitrite. So it really is this phenolic thing. Okay, so you get the idea. So let's get to the business. If I sweep the voltage across these electrodes, I see various different features of current being passed through coffee. And so people have studied the chlorogenic acid response, that's in this area. They've studied caffeine, it's in this area. But you'll see then there's all these little bumps down here that have never been reported. And so this is where my group has been working, is can we use these bumps to tell us something about the composition of coffee as a direct measurement? And the short answer is yes. Let me explain to you what those features are. You start out with water that is slightly acidic. You stick electrodes like platinum in there, and the first thing that's going to happen when you make the electrode negatively charged is the water is going to reorient. It's going to get electrons accumulating, and at some point, the protons are going to start to absorb because the plus and the minus are attracted to one another. And then at some point, your surface is going to be completely covered with protons, but they haven't formed hydrogen yet. So that process is depositing hydrogen. And now they're going to start to combine, and at some point, you're going to desorb hydrogen, you're going to make hydrogen gas, or bubbles. So if you were to impede this process by covering the platinum surface in molecules that were not hydrogen, for example, stuff in coffee, then what you would see is a decrease in the amount of hydrogen available to absorb. Something like this. This is blocking the surface. Now it turns out then that stuff ends up stuck to that platinum surface pretty strongly. And people have actually used this. So in the 1970s, they proposed that you could just stick platinum in water and apply electricity. And over time, the platinum would just absorb all of the organic molecules that were floating around in solution. You could use it as a water purification technique. We're going to do it. Yes, coffee is really, really dirty water. And so we're going to basically use the same approach where we're going to apply a potential. We're going to observe a decrease in current associated with this stuff sticking to the surface. So what you then might do is you might brew up some coffee. You might make sure that it's all the same TDS. And you'll note this is a pretty dilute, but you could do this at basically any concentration. And in just one sweep, you're able to very readily see that there's a difference in the these are all the same Colombian coffee, but roasted by different people around the world. And you'll see then they start to form little groups. So these A's these were indistinguishable from one another. Tim Windlebow sticks out, and then Passenger and Reverie had similar composition, something. Whatever was sticking to that surface was similar. But it turns out it's not as simple as just a single sweep. So because every time you sweep, you accumulate more stuff. You expect that subsequent sweeps are going to result in even less surface area being available of the platinum. And so what we use is the difference in the first amount of current to the second and the second to the third. And those differences tell you the rate of adsorption of molecules to the surface. And if you remember that at the very beginning I said that rate is what matters, and Shahan's work showed that, this is a direct measure of how fast molecules in solution are making their way to that surface. Nice. Okay, that's good. So then, the very simple experiment you can do is you can basically just dilute. And if you dilute, you'll find that you see less and less current. And this perplexed me for a while because I assumed that if you had more material floating around, that you'd have more stuff rapidly sticking to the electrode. So you'd expect to see less current. But it turns out that remember what we're measuring is hydrogen atom adsorption. So if you go more dilute, there's just less hydrogen around because there's less protons because it's more dilute. So this is an obvious observation. But it does mean that if I just integrate there, that should be linearly related to TDS. And it is. We just made a fancy TDS probe. Though it's not what the world needs, but it's what the world got so far. So then I had to roast. And I know obviously nothing about roasting. So I did what most people do, and I contacted Scott Rayo. And he told me that these temperature curves mean nothing, and I disregarded that comment because I couldn't do anything with it. So instead, I just used these temperature curves, and I assumed that this is the lightest one, this is the darkest one. Indeed, it's true. They were lighter. That was lighter than that one, okay? But they were more or less systematically different in my mind. At least from a scientific perspective, I just made them 30 seconds longer at 2 degrees higher end temperature. It worked. Nice work from Shahan yet again showed this, that if you roast in different speeds to different colors, you end up with different composition. This paper here was monitoring CO2, but CO2 is just sort of a touch point for all the other molecules generated during the roast. And this is something that was touched on by Rob in a very nice way, basically saying how you get to the endpoint does tell you something about composition. They do taste different, even if they're the same color. Okay, fine. So all that in mind, what you do then is you brew up the coffee, different roasts. You then do these sweeps of voltage here, all right? And then for the same TDS. And what you'll back out then is that dark coffee has a lot more stuff that sticks to that electrode than light coffee. And as a result, you can then construct you can measure how dark something is. I use the dipper, but if you have more money than me, you could probably buy an Agtron. And if you do that, you're able to create a plane where you have TDS as measured on the optical device, Agtron color or beam color, either whole or ground, and charge passed, and you get a plane here. Now this plane allows you then, with knowledge of the color of the coffee and a quick electrochemical measurement, to back out TDS, or to measure TDS and to then use to predict the EChem. And if the EChem doesn't align with the TDS, then you know that composition has gone totally haywire. All right? Good. So that's fine. But I want to then go into the real power of the technique. So I mentioned that molecules stick to the electrode surface, and we can reversibly oxidize and reduce them. But what if we choose to not do it reversibly? What if I choose to sit at, let's say, minus 0.3 volt for 25 seconds and just destroy whatever happens to swing by that electrode? Okay, so if you open up a corked bottle of wine, there are a lot of different molecules in wine that can taste like wet dog, cardboard, etc. But I'll pick one that's redox active here. This is the one on the left. If what you do is apply 2 electrons, so you add 2 electrons to it, so that is reducing this compound, you can take a corked bottle of wine to tasting something like nectarine lavender. So all you need to do is put your electrodes in, apply a very small amount of voltage for a short period of time while stirring, and that molecule is dead. It's gone. How about this? You have a bottle of beer or something that has Brett taint. And Brett produces a very well-defined functional group, this functional group here. Well, this functional group actually happens to be very redox active. And indeed, if you apply electricity, you can decompose this molecule into ethanol and CO2, which is interesting because if I'm drinking a beer that has this molecule and I don't like it, all I do is stick my electrodes in and I make more ethanol and bubbles, which is good. So, all right, so I got one more. Let me just give you a couple, this is sort of a sneak peek here. What if I had a molecule you couldn't taste, but upon applying electricity, I could break it into something that was the most grape you've ever had in your life? That'd make a cool signature drink. Okay, fine. How about this one? A little bit blueberry, but you want it, maybe perhaps you're trying to hide defects like we just heard about. Maybe you want to find a way to correct for a lack of flavor. Apply a little voltage and crank it up so that now the coffee is more valuable because it has a flavor note that maybe outweighs all of the negative ones. I don't know. There's a lot of applications. How about this? How about a more simple one? We use the method to say what the TDS is, and then we apply a little voltage to correct for sweetness and acidity. We ran the sensory experiment in Italy at the end of last year. We got our data. I'm not going to present it to you today because we're still, I'm rigorous with how I do this. I want to make sure that what I'm presenting is really solid. But I can tell you that the panel that tasted this knew immediately that when we applied a very small amount of oxidizing potential, we could scoop out acidity. When we sat there for longer, and we could bring back in a very unusual and perhaps maybe appetizing different type of acidity. So we have a way of affecting your perceived acidity, and at higher voltages, we could do it with sweetness. So with that, it's a long journey just to sort of wet the whistle for what's to come. And what is to come is, I would like to say, my most valuable contribution, hopefully it will come this year, which is using electrochemistry to directly measure composition. What I didn't tell you was how long it takes to make the measurement, and that is 0.01 seconds. So it's fast enough that you could integrate it directly into an espresso machine and self-correct as the espresso shot is coming out. It's fast enough that you could do it to every single cup in the cafe. You could build the electrodes into the cup, so you could have like a metallic ring inside each one. The opportunities for this are endless, and as per normal, what I really want to do is put it in the wild and see what people do with it. So that's what's coming this year. I know it was a long journey. We started out by talking about Buchner and his observation of yeast fermenting ethanol. And we ended up with me talking about roasting. Obviously, I have no idea what I'm doing. I'm going to do the class tomorrow. It'll be awesome. And then, but also showing you that electrochemistry is a playground. And in one sense, we can measure roast color with a device that is not optical, which is good. We can also affect flavor. We can also, in principle, measure one of the key flavors, which is roast, right? The amount of development, the color of the coffee. So with that, I just want to say that the summary of what I've talked about is that we apply voltage to coffee, we measure current, and that tells us something about what's dissolved in the cup. With that, a lot of people have contributed as coffee donors. If you're thinking about you want to get involved, my lab really benefits from 5 pounds of coffee from whatever coffee it is, even an off batch. Like let's say you roast something, you're not going to send it to me because we use it, we crush that stuff. Okay. The next thing is that electrochemistry is tough. This is an exposure therapy thing. Okay. I got to keep showing you it. And at some point you're going to go, I got it. But there are much more smart and talented people than me who've worked on this. I recommend reading this open access paper by Jillian Dempsey at UNC Chapel Hill. It's in JChem Edu, and it explains the basics of electrochemistry. This is going to be really, really helpful. So I'll give you a minute to have a look at that. And then finally, this work is funded in my lab through the Coffee Science Foundation. Without them, we wouldn't be able to do any of this exploratory blue skies work. We're trying to do things that are new and different to what the industry is used to. And the money itself came from Nova Simonelli. All of you know them. Obviously a company that is philanthropic and interested in pursuing new types of science for the greater good of this community. So with that, I hopefully have a little bit of time for questions. Thank you very much for the invitation to speak once again. It's my pleasure.